Hi, in this video we're going to discuss a topic in probability and statistics that we frequently don't get time to do in class, and so I'm going to do a short video to give you an introduction to Bayes' theorem and Bayesian thinking. This topic goes back hundreds of years to a Church of England clergyman, Reverend Thomas Bayes, and here's his picture. In addition to being a clergy, Thomas Bayes studied probability and mathematics. And to give you the context of his work, remember the conditional probability formula, probability of A given B, can be written like we discussed in class, the probability of A and B happening together in the numerator, and the probability divided by the probability of B down here in the denominator. And the fraction of these two probabilities turns out to be this conditional probability of A given B. Well, in this expression, if you multiply both sides of the equation by the probability of B, you can isolate that the probability of A and B happening together is just this product of the chance of A given B times the probability of B, this multiplication. Well, the Reverend Thomas Bayes noticed that if you would just reverse the order of the event and the condition and put B to be the event and A to be the condition, you could use the conditional probability law to have the probability of A and B together divided by the probability of A. Multiplying both sides of this equation by the probability of A gives you the isolation that A and B together chance could be written as a product of B given A times the probability of A. Well, Reverend Tom decided to plug this expression, B given A times the probability of A, up into the numerator of the original one, and this new formula became known as Bayes' theorem. The probability of A given B is simply the probability of B given A times the probability of A divided by the probability of B. Now, this might seem just like sort of a trivial rewriting of some algebraic axioms and that nothing particularly interesting happens because of it, but there are some really amazing implications of rewriting these conditional probability expressions in this way. So here's the formal expression of Bayes' theorem. The probability of outcome A given that outcome B happens can be expressed as the reverse probability of B given outcome number 1 of A times the probability of outcome number 1 of A divided by the overall probability of B, known as Bayes' theorem. A rewriting of Bayes' theorem, expanding out the little parts in the way that you can construct the probability of B in this denominator by basically the intersection of event A1 with B and event A2 with B and so forth, basically putting together all the parts of the total probability of B is another way of writing Bayes' theorem either way. That's the formal expression of the theorem. Here's how you might think about using it in a simple context. Suppose you've got two bowls of cookies. Bowl number 1 has got 10 chocolate chip and 30 plain. Bowl 2 has 20 of each. Someone named Fred picks a bowl at random, and then out of the bowl that has been chosen, chooses a cookie at random. We should assume no reason to think that Fred, our person, would choose one bowl more than another, and so without any information, you would presume that Fred would choose bowl number 1 with probability a half, bowl number 2 with probability half on the initial bowl selection. Let's suppose that at the end of this study we find out that the cookie that's chosen is a plain cookie. Here's a question we could ask. What's the probability that bowl number 1 was the one selected, given that a plain cookie was the one ultimately reported to be drawn? What's the probability it came from bowl number 1, given that a plain cookie was drawn? Reasonable question. Here is how we can do it. We need to find the probability of bowl number 1 given a plain cookie. Well, using Bayes' theorem, we can find the probability that a plain cookie was drawn given that bowl number 1 was chosen. Remember, bowl number 1 had 30 plain cookies out of a total of 40. So this first probability is pretty easy to get. It's 3/4, 0.75. Remember that our original opinion about the probability of selecting bowl number 1 is a half, so in the remaining part of this numerator is just a half. So we have 3/4 times a half for this numerator. The denominator is a little bit more complicated to get, but we could make a two-segmented tree diagram. Have bowl number 1 be the first branch going up, bowl number 2 be the first branch going down. Again, probability a half on each of them. And then on each bowl, draw plain and chocolate chip and go through the choices and the outcomes for adding up the total probability of a plain cookie being drawn. If you make your little tree diagram, you can observe that the upper path to a plain cookie is a half for the first branch of bowl 1, and then 30 out of 40 for the plain cookie. That's the top path, multiplying the branch probabilities. The other path to getting a plain cookie is drawing bowl number 2, and then a 50-50 chance of getting a plain cookie. And so your final probability of drawing a plain cookie out of this collection is 0.625. Put that down in the denominator of Bayes' theorem, and you get a final probability of choosing bowl number 1 initially of 60%. And hopefully this makes some sense to you. Before we started this adventure, we would say there's a 50-50 chance that bowl number 1 or bowl number 2 would be drawn when they're choosing randomly. But the information added to the problem by knowing that a plain cookie was the one that was drawn shifts our opinion slightly towards the fact that bowl 1 was chosen, because there's an awful lot more plain cookies in bowl 1 than there is in bowl 2. And so the knowledge of a plain cookie being drawn shifts our opinion about bowl 1 being the original bowl. It's not 50-50 anymore. It's a 60% chance in favor of bowl number 1. And so this illustrates the idea that Bayes' theorem helps us modify our original opinion about which bowl was drawn. We modify our opinion given some little information about the experiment. A plain cookie being drawn changes our opinion slightly about bowl number 1. And that's basically the beauty and the usefulness of Bayes' theorem. You have a homework problem that uses this idea. It's the Julianne is a carrier for cystic fibrosis problem. Remember, in that problem, before she has any children, there's a 2/3 probability that she's a carrier. But as you go through the problem using the information that a child was born this day without cystic fibrosis, the conditional probability of her being a carrier given a child with no cystic fibrosis moves this probability of her being a carrier below 2/3. Every additional child she has lowers the probability that she's a carrier. You know, if poor Julianne would have 4 or 44 children without, every one of them without cystic fibrosis, that would move her probability of being a carrier systematically towards 0. And that is the idea of Bayes' theorem. It lets you update an opinion about an event given some additional information about the context. Overhead 82 is sort of the formal way that statistics uses Bayes' theorem. There are basically 2 ways that statisticians think about statistics: the frequentist way of thinking and the Bayesian way of thinking. And these two ways of thinking are in big conflict and do not get along within the statistical community. Just for the record, the flavor of statistics that you're currently being taught is the frequentist way of thinking about statistical work. It will probably remain to be the way most introductory courses are taught for at least a couple, 3, 4, 5 more years. But eventually the Bayesian way is going to win and be the way that this course is taught in the future. To give you an idea about how it's just not quite ready yet, but it will be, and at some point the Bayesian way of thinking about statistics will be what's taught. Here's a little bit of flavor about why it is such a conflict and so controversial about which way you do statistics. Think about an easy problem about a drug that cures a particular condition. The unknown fraction of patients that are cured by this drug is an unknown quantity called P. A Bayesian way of thinking about this would be to find the probability distribution for the cure probability given some data on patients. Well, Bayes' theorem says what we need to do is figure out the chance of observing the data we do on patients given a particular cure probability. And that's really easy. That is some kind of big tree problem. And this first part of the term is quite easy to get. Similar sort of way of getting this denominator. It's sort of a long problem, but it's doable. The conflict really comes right here in the second part of this numerator. What is the probability distribution for the unknown cure probability? Well, it's kind of a guess, and it's subjective opinion. And frequentists absolutely have a fit and get very angry that scientific work uses subjective opinion and just personal knowledge about what this cure probability is before we do any experiments or any data. It's like a prior guess or a prior opinion about how effective the treatment is going to be before there's ever any patients. It's called the prior probability. Frequentists really object to this. Bayesians would say, well, a new drug or a new treatment is probably going to be slightly different or maybe quite a bit different than old treatments, and we should have some guess from past experience or other experiments related to this. We probably know something about what the cure probability ought to be, or at least close. And Bayesians would say, why don't we use that and then just update this opinion using some new data from an experiment. Kind of like we did with the cookie example. We have a prior opinion about which bowl would be drawn, and then we'll use data to update our opinion. Why not do that? And that's the idea behind Bayesian thinking. On this overhead, 83, is sort of the basic philosophy that I've mentioned, the second expression right down here. If you want to know what's the new opinion about buying a product at Amazon.com. By the way, Amazon.com uses Bayesian statistics to figure out the probability that you would buy a particular product. They have calculated this. And what they do is they use your past buying data to come up with a probability distribution for the probability that you'll buy a particular product given your buying history. And the way they update their opinions is every time you buy something on Amazon, they have a way to calculate what's the probability that you would have a new purchase the way you did, given the old probability for buying a product, and you would use that to update the probability distribution for the probability of buying a particular product given your past buying history. And in that way, Amazon.com uses new data to update their probability distribution on a new product that you would buy. This same principle is applied in a very good film called The Imitation Game, using data to decode the Nazi World War II code system. Amazon.com uses it. It's being used to find lost airplanes in the ocean. They'll use search data to update their opinions about where a plane is located. And so by doing some searching, you can modify the search area given other data. And this is really the secret behind Bayesian statistics. Using new data to update an opinion about a particular thing of interest, like the probability of purchasing a product or the probability of a location containing an airplane. Bayes statistics is really the way the future is going. It's already going this way. Eventually, introductory statistics will teach you this way of thinking. It's very complicated mathematically, and we need some better computational tools, but those things are being developed, and at some point we'll be using this way of talking about problems. Let me know if you have questions about how this works.